This is VLSI data conversion circuits, lecture 34. In the last class we looked at what the effect of one important non-ideality in continuous time delta sigma modulators, illustrated here with a SIF type loop filter. We saw that in practice the ADC DAC system will not be delay free, and this is delay that we did not anticipate during the design of the loop filter for a specific noise transfer function, and therefore this extra delay that the ADC DAC path adds is what is called excess loop delay. In the simplest of cases we saw that it could affect the stability of the loop. This makes sense because every time you have a feedback loop, if you deliberately introduce excess delay in the loop, from experience we know that the loop will tend to become unstable. Even if the loop does not become unstable, if because the delay is very small, we saw that the performance of the loop can become altered in the sense that even though the signal band noise transfer function remains the same, outside the signal band crazy things could happen in the sense that the poles of the closed loop system are not what you originally intended them to be. In the case of first order modulator, we saw that if we make tau the excess loop delay equal to 1, the poles are actually on the unit circle, and you can only imagine what happens when the order of the noise transfer function that needs to be realized is higher. We also saw what one can do to fix this problem, and that involved adding a feed forward path across the loop filter, which can equivalently be interpreted as a direct path around the quantizer. We also saw how one could calculate the coefficient of this direct path and the values of the coefficients which have to be modified in order to bring the noise transfer function back to the desired value in spite of this excess loop delay. Alright. Today we will take a look at couple of other non-idealities that occur in continuous time delta sigma modulators. The first one is what is called clock jitter. So, if we kind of look at this path a little more carefully, ideally what we expect to happen is that there is an A to D and a DAC. All right. The A to D basically samples, let us say, at the rising edge of a clock. All right. So, this clock is what is controlling the sampling instant of the A to D converter. Ideally, mind you, the D to A converter would also be controlled by the same clock, and the output waveform of the D to A converter will occur exactly at the sampling instant of the A to D. In other words, we are assuming that the A to D converter looks at the input, figures out which of the bins of the input characteristic the incoming input lies in, generates a digital code representative of that input, that goes to the D2A, the D2A puts out a continuous time waveform corresponding to this input code, and all this happens in 0 time, right. Clearly that is not possible. So, there is the first non-ideality, as we saw the last time around, is excess delay. In other words, one can interpret that as the A to D makes some time to make a decision and passes it on to the D2A. The D2A takes its own sweet time and generates the output pulse. All that can be modeled as if the clock to the D2A converter is delayed by some Td. In other words, in this diagram, both the A to D and the D2A are assumed to have 0 delay, right, but we deliberately clock the D2A a Td later in order to model the delay of the ADC DAC path. Okay. Yet another non-ideality that we are going to talk about now is what is called clock jitter. Right. So, when we say clock jitter, what we mean is that the edges of this clock that we use to sample the input, which needs to be quantized, as well as the delayed version of the same clock, which goes and clocks the DAC, and the output of the DAC is synchronous with the edges of the input clock that it sees, correct. It turns out, unfortunately, that these edges are not occurring at the exact period that we think that we want. For example, if we say the input clock rate is say 1 gigahertz, we would expect every rising edge of the clock to occur precisely at multiples of 1 nanosecond. What happens in practice is that the oscillators or the systems that are used to generate these clocks are noisy, which means that on the average every rising edge will be apart by a nanosecond, but instantaneously they may be from edge to edge, they may be, the delay may be off, all right. In some cases neighboring edges may be let us say the time interval between neighboring edges may be say 999 picoseconds, and the next two set of edges it will be say 1001 picoseconds, right. So, in practice what happens is that this all that one can say is that the average delay between adjacent rising edges or adjacent falling edges is 1 by Fs, right. However, the instantaneous values, that is from edge to edge, may vary according to some distribution, right, and that distribution and the variance of that process depends on how the clock is generated. All right. We will not go into details of that in this course. All that we will say is that the clock edges are jittery. The fact that the edges are not exactly periodic is called jitter and is often referred to as clock jitter, because these edges are pertain to a clock, all right. So, if there is jitter, there are two things which are happening. What all in what all ways does the jitter in the clock affect the system we are looking at? If the edge is not at the right time that is supposed to occur, let us say before or after, okay, slightly. Please note that these are all very small deviations from the nominal time period, okay. So, if the edge is slightly displaced from its ideal value, what do you think will happen here? All that happens is that the A to D converter, instead of quantizing a value at a certain time t, will quantize the input which is at t plus some delta t, all right. In a similar way, if this H jitters, the clock here is simply a delayed version of the input clock. So, if the rising edge jitters, it will also affect the D to A converter clock by the same amount. So, what does that mean? What is the implication of that as far as the D to A converter output waveform is concerned?
So, you can model that as the delay in that loop, right?
No. See, the suggestion is that why do not you model this as a delay in the loop. I mean, if this was a fixed number, then we would say it is equivalent to a delay in the loop, but this is varying from edge to edge. So, this cannot be modeled as a delay in the loop. Is that clear? Okay. Now, if the edge to the DAC is jittered, what do you think the effect will be at the output of the DAC? So, the output DAC, which let us say was supposed to rise at a certain time, will now rise either a little, just a little before or just a little later compared to the ideal rising time. Okay. So, let us try and understand what the effect of this is on the performance of the modulator. Is this clear? Okay. So, let us summarize the discussion so far. Let us say this was the input to the ADC. The ideal sampling instants are these times. Okay. Now, the actual sampling instant, because of jitter, is say this. Please note that I am grossly exaggerating here, so that the displacements will be visible. And as you can see, the two of them are in error. If I call this delta t, then the error in the sample is proportional to approximately, what is the difference between the ideal sample and the actual sample that you get? It is simply the error in the ADC input is simply delta t sub n, which stands for the jitter in the nth clock edge, times d y of t by dt evaluated at t equal to NTS. Please bear in mind that the input to the ADC is y of t. All right. For simplicity, in this course we will simply assume that the jitter sequence delta t sub n is white Gaussian distributed right, and let us say its bandwidth is such that it is very broadband and for all practical purposes can be thought of as white, and it's the variance is sigma delta t square. Okay. So, delta t sub n is simply a discrete time sequence which is Gaussian distributed, has a variance and it is white, which means that the jitter in subsequent edges is completely uncorrelated. You understand? Now, if the delta t sub n is uncorrelated from edge to edge, can you comment on this error? It will again be white. Okay. Does this make sense? Because each of these numbers is uncorrelated with each other, which means that if you find the average of two numbers which are like this, right, by virtue of these being uncorrelated, the delta t's being uncorrelated, the average value of this sequence will also be 0, right, which means that the errors are also uncorrelated. Okay. Now, so therefore, you can model the effect of sampling jitter in the A to D converter by adding a sequence E sub n, where E sub n is nothing but delta t sub n multiplied by the slope of y at the nth clock edge, right. So, in other words, an A to D converter or an ADC sampling the input y of t with a jittery clock can be modeled by the same A to D sampling with a clean clock, but the error due to jitter represented as an additive sequence at the input of the A to D. Of course, in this particular case, because of the assumption we made on the nature of the jitter, this E sub n is a white sequence. All right. Now, what do you think will the what do you think the effect of this will be on the performance of the modulator? So, recall that what we need to do is to replace the ADC at the input by an ideal sampler followed by an additive noise source which is white.
This can be assumed to be adding some noise to the quantizable.
Yes, yes.
It will be shaped.
So, correct. So, the question is, as you rightly guessed, right, this is equivalent to, this is exactly the place where you are injecting quantization noise into the loop, right. So, if you inject a little more noise, it will also be shaped by the action of the loop just like quantization noise, and please note that quantization noise is the variance of the quantization noise is delta square by 12, right, which is much larger than the variance of the jitter noise. Okay. So, as far as the A to D converter is concerned, E n is shaped by the feedback action of the CT delta sigma loop. Is this clear? Now, the next thing that we need to worry about is what happens to the so this is taken care of. We need to worry about what happens with the DAC. Now, please remember that the DAC receives the digital input code from the A to D converter and is ideally supposed to put out a waveform V of t, which is synchronous with the DAC clock, which is nothing but a delayed version of the ADC clock, and these edges are jittery. All right. So, if the clock was not jittery and let us say Vy was V of n rather was this sequence, assuming a non return to 0 DAC, what would be the output waveform look like? It would simply look like this. All right. So, this is V of n, V of, let me call this V of n minus 1, this is V of n, this is V of n plus 1. So, the ideal continuous time waveform should look like this, assuming a non return to 0 DAC. Now, what is happening? The edges are jittery. So, let us say without loss of generality, for example, that this edge comes too late, this edge comes a bit early, and this edge also goes late. Okay. I mean the DAC does not know what is happening, every time it sees a clock edge the output changes value. So, the jittery waveform will look like this, right. So, what is the error between the ideal waveform and the jittery waveform? What is the difference? Let us say ideal minus actual, or let us say the error is nothing but the actual minus the ideal, I am sorry, is the error waveform, correct. And how will the error waveform look like? So, during this interval, how will it look like? It will be 0 until the actual waveform rises, then the error will do this and then come back. Then what about at the next stage? It will be negative. Oh, first ideal minus actual. I am sorry, actual minus ideal is what I want. Yeah, both will be positive. I think that's true. All right. Let me draw that cleanly. So, if I look at the error here, you can see that it is what is the width of these pulses? It's only delta t n, this is delta t n plus 1. Okay. What is the area of these pulses? Please note that the width of the rectangular pulses is a pulse with a width equal to delta t of n and a height v of n minus v of n minus 1, correct. So, one can therefore model the DAC as a DAC which is being driven by an ideal clock which is jitter free, all right. And to this one is adding an error waveform E of t, right, where the waveform can be thought of as being, for instance, is sigma, let us say E n of t, or E n is the nth error, right, times, how do you think we can represent this error? Go back to your networks classes, you have a pulse which is basically very, very thin and has some area. How do you think you can represent that as? A Dirac delta, right? You can think of it as E of n delta of t minus n t s, where E n is delta T n times V of n minus V of n minus 1. Does it make sense? So, let us see what happens in a real, I mean when you try and understand the effect of jitter in the clock when you embed this in a delta sigma loop. Please notice one thing, if there is no change in the sample from clock cycle to clock cycle, it makes sense that the error you add is 0 even if the clock jitters, because the next sample is the same anyway, all right. In other words, if two subsequent samples are the same and if we had an NRZ DAC, then there is no error due to clock jitter.
Sir, this En dimension should be voltage, right?
E n dimensions should be voltage, yes, that is correct.
But delta Tn times Vn minus Vn minus 1 is not voltage.
No, E of n is this delta T n times V n minus 1, correct, and the dimensions of this will multiply and you will get, all that we are doing is we are saying that this area corresponds to the area of the impulse, that is all. Okay. Now, let us see what this does to the modulator. I am going to copy and paste this diagram. All right. So, we already saw that the error due to the ADC is of no consequence because noise shaped. What we are interested in now is the error due to the jitter in the DAC. All right. let me call this E DAC of t, which can be approximated as sigma delta T n V of n minus V of n minus 1 delta of T minus n T s. All right. Please bear in mind that delta T sub n, which is the jitter of the nth clock edge, is a white sequence by assumption, and therefore, this sequence is also white. Okay. Now, before we get into the details of what happens to the output SNR, what do you think will happen? Do you think E DAC of t is detrimental to the operation of the loop, or this is also of no consequence, just like the error in the A to D converter path? Pardon? Yes. So, correct. So, please note that this can be interpreted as adding something directly to the input of the modulator, and therefore, E DAC of t, right, at least the low frequency component of it will come out directly, because the STF at low frequencies is 1. Okay. So, unlike the error due to jitter in the ADC path, which is noise shaped by the loop, the error due to clock jitter in the feedback DAC path is a serious problem and will degrade the performance of the loop. Is this clear? All right. Now, let us try and understand what this sequence looks like. Finally, what frequency components of this are we interested in? We are only interested in those components of this waveform at low frequencies, that is those frequencies which are inside the signal band. All right. So, and please note that because we have impulses, this actual signal consists of very high frequency components also, but we are only interested in band signals, correct, because the STF of the in band signals is equal to 1, and stuff which is out of band will anyway get filtered out by the decimation filter after the, which occurs after the delta sigma modulator. Is this clear? Now, as far as low frequency signals are concerned, an impulse train like this is exactly equivalent to, let us call this area A1, A2, A3, which are the strengths of these Dirac impulses. If we are only interested in low frequency content, right, we can represent them also by NRZ pulses like this, as long as the what is the meaning of low frequency content? Okay. Do you understand my assertion here? I am claiming that as far as low frequency content is concerned, both these waveforms are identical. Yes? No? Okay. Given this waveform, how will I generate this waveform? No, it's not integrate. With what impulse response? If the input sequence to a filter is this and the output is this, yeah, so it's u of t minus Ts, right? So if this is say Ts, this is 2 Ts, 3 Ts and so on, you can think of this waveform as being generated by this waveform passed through a filter which is 1 here and lasts up to Ts. You understand? Okay. If you want the low frequency content of this to be the same as the low frequency content of this held waveform, what do you want the gain of the filter to be at DC? You want it to be 1, right. So, you should choose this to be actually not 1, but 1 over Ts. In other words, as long as the area of this impulse is the same as the area of that rectangle, the low frequency content, which is nothing but the average, will remain the same. Is this clear? That is the intuition. When you low pass filter, what are you doing? You are just averaging, correct. So, whether you have a sequence of impulses with a lot of high frequency content or whether you have a sequence of rectangular pulses, as long as their areas remain the same, at low frequencies they will have the same spectral components. Okay. What do you think is the motivation for this interpretation at all? Why do we need this? So, I mean, we know that the DAC is putting out V of n times this rectangular function. Now, we are modeling the error also by an NRZ type waveform, which means that instead of talking about E DAC of t, one can refer this to the input of the DAC and think of it as an error in V of n itself. You understand? Okay. Does it make sense? So, what must be the sequence that you must add to V of n? It is simply the area of those impulses, which is delta t sub n times V of n minus V of n minus 1 divided by Ts. Correct? So, this is the error sequence that will be produced at the output of the modulator. You understand? Right. And what kind of sequence is this? This is also white because this sequence is white, all right. And this is telling you that the larger Vn minus Vn minus 1 is, the more the error will be at that sample. Okay, this makes sense because the DAC changes by a lot from sample to sample, and with the edge jitters the error you are adding is proportional to the change multiplied by the time jitter, delta Tj, all right. So, without getting into the maths, if the output sequence is in error by in other words the actual sequence is the ideal sequence plus a noisy sequence which is white, what do you expect will happen to the output spectrum? Let us say the ideal spectrum was like this, okay. To this you are adding white noise. So, what do you think will happen to the in band frequencies? So, this will be the stuff without jitter. With jitter you can expect something like this. Well, it will, but this being on log scale is so small that when I add it to the shaped quantization noise, it just will pale in significance, right. So, if the jitter variance goes up by 3 dB, the in band noise will go up by 3 dB due to clock jitter. So, the total in band noise will consist of the shaped quantization noise plus that due to clock jitter, and it turns out that the loop filter itself will be noisy because of transistors and resistors and capacitors and stuff in the loop filter. Therefore, the loop filter will add its own noise. So, the total noise at the output will be the sum of all the three: quantization noise plus jitter noise plus thermal noise from the loop filter. Okay. So, we will calculate the variance of the noise due to jitter in the next class.